All right, so let's chat improper integrals. This particular integral, we're looking at finding the area under the curve for a lovely shifted version of our x squared graph, 1 over x squared, or a reciprocal squared graph, which will look like this. So there's an asymptote at x is equal to 3, and we're trying to go from 0 up until that asymptote and see if that area under the curve converges or diverges. What happens? Is this a number? Can we say something good about it? Or is this going off towards infinity? So in order to do this, we first need to rewrite this in terms of a limit statement, because the fundamental theorem of calculus does not let us write or use the fundamental theorem of calculus unless we happen to know that we're dealing with a continuous finite situation, and we are not here. So first we need to do is rewrite this as the limit. We need to replace that upper bound because that's where our problem child is happening, right? That's where our asymptote is at. It's at that 3, so that's what needs to get replaced. So we're going to go ahead and replace it. In fact, let me just rewrite my integral right here. I'll have the 0. There's no reason to change this. 0 is not a problem on my graph at all. We have our 1 over x minus 3 squared. You might want to rewrite that as x minus 3 to the negative 2, whatever floats your boat, dx. And we do need to have the b in the place of the 3. I saw a lot of people actually write out the b and not in the limit notation, and then leave a 3 floating as their bound. So that needs to be b. And then we know b needs to go to 3. And we are approaching 3 from the left-hand side, so we need that little negative symbol. So if you had this, that was essentially 2 points. 1 point for rewriting the bound that we cared about, that upper bound of 3, and 1 point for recognizing that we needed a direction on that limit notation because we were only approaching that 3 from a particular side, and that side had to be from the left, so we needed a negative. The next piece of points here, we're continuing and having correct communication when evaluating this antiderivative. So if I thought about this off to the side, maybe with a little floaty math as an x minus 3 to the negative 2, yes, I could do a baby u sub, but I know we don't need to. I know I'm going to end up with an x minus 3 to the negative 1 over negative 1. And I'm going to need to evaluate that at b and 0. Now I have not evaluated it yet, so it's super crucial that I still have that limit as b approaches 3 from the negative side. Okay, now I could actually apply the fundamental theorem of calculus, plug those in, do what that evaluation line is saying. I need to have, in fact, maybe let's go ahead and rewrite this so that we can kind of feel what's going on a little bit more. Since our x minus 3 is to the negative 1, let's go ahead and write this in the denominator. B minus 3 minus, but it's going to become plus 1 over 0 minus 3. Now again, we haven't dealt with the fact that we don't know what happens when we actually evaluate this at 3, so we need to keep our limit symbol. Cute. Okay, so now is the moment of truth. We have to notice, right? And so if you had done all of this, you've gotten 3 points. The last point was for figuring out whether or not the interval converged or diverged based on all this information. And so we could recognize and look here, if I plugged in 3, which we know is not really what's happening, but if I did plug in 3, I would have negative 1 over 0, and a number divided by 0 we know diverges. This goes off towards either positive or negative infinity, depending on that, what's happening with that 0. So it doesn't matter that I have a cute value for that second term, that first term diverges. So we could go ahead at this moment and say our original integral, as improper as it was, oops, I got caught between writing a parenthesis and a square, diverges. Now, if we want to be a little bit better about that, because we can actually see, right, if we look at our graph, it looks like if this thing diverges, it's going to be a positive infinity, right? This is all above the x-axis. It looks like it's getting really, really large. And also, if we think a little bit more about that p-series sort of situation we chatted about in class, we might recognize that we're going to end up in this sort of trouble anytime we're dealing with a vertical asymptote and we're dealing with now a p, a power in our denominator, that is greater than 1, because that's going to leave that problem child, what happened here, the 0 in our denominator, whereas the contrary of what we wanted before, right? If it's a fractional value, we'd be able to bring it up when we add 1, right? So if this had been a 1/2, a square root, when we added 1 to that negative 1/2, we would have ended up in the numerator, and then a 0 is completely fine up there. We wouldn't have had any trouble. But anyways, let's think about what's happening. If we're approaching 3 from the left-hand side, we're approaching 3 from smaller values. So imagine that. We're plugging in like 2.9 minus 3, and then 2.99 minus 3. So each and every one of these is negative, right? We have a negative 0.1, a negative 0.01. And when I divide that through with the negative that's in the numerator, a negative divided by a negative is positive. So this whole term is going to positive infinity. And positive infinity minus 1/3 is essentially positive infinity, right? So this does actually match what we're seeing in our graph. I had some students who actually attempted to see if this was they wanted it to be a negative infinity because they knew a number over 0 is infinity and there was a negative on this, but it didn't match what was going on in the graph. So I wanted to just take a moment to chat about why this ended up being positive infinity and maybe give us a little trip down memory lane from Calc 1.